Well, it appears I wasn't quite done with number 40. So here 40D, and once again you'll notice that the more electrons we add, the greater the size, the greater the atomic radius or ionic radius of this. And then tellurium, selenium, sulfur, and oxygen are all in the same family. And so tellurium just has a lot more electrons, so it's going to be larger. Now, as we went through Chapter 8, you may remember we looked at this idea that if you want to know information about the energy that it actually takes to produce sodium fluoride solid from solid sodium and fluorine gas, you can look at a series of steps. You know, the sodium has to be sublimated, the electron has to be removed from sodium, the fluorine bond has to be broken apart, the dissociation of the fluorine molecule, and then the electrons have to be added to fluorine to make a fluoride ion, and then the ions have to move together, and those last two processes are exothermic, and so we end up having an overall exothermic enthalpy for this reaction. And the greater the charge differential, the greater that lattice energy will be. And so here with magnesium oxide, very high lattice energy, so we'd expect to have really high melting points. And that higher lattice energy and higher melting point is a result of the greater charge differential. Magnesium oxide is 2 plus and 2 minus, as opposed to sodium fluoride is 1 plus and 1 minus. So in problem number 45, that's what they're looking at here, is the energy of sublimation was given to you. That's where we're changing potassium from a solid to a gas. Here we're ionizing the potassium, putting in energy to strip off that electron. Here we're breaking the chlorine bond apart. Now notice here we're only going to do half of a Cl2 because that's what we have down here in our final equation that we want to have balanced. And then we have the negative change in enthalpy when the electron is added to the chlorine atom to make a chloride ion. And we have the lattice energy, the energy that's released when these things come together because they're so much attracted to each other. So if we add all of those together, we get a change in enthalpy of negative 437, indicating this is an exothermic reaction. And so that's how you can predict the change in enthalpy of formation, because remember, that's really what this is this is change in enthalpy of formation of this substance, because here we see potassium and chlorine coming together to make potassium chloride. So number 46, this must be 46B. Gave you similar information for magnesium, and one of the differences you'll notice here is there are two ionization energies. The energy required to remove the first electron is ionization energy 1, and the energy required to remove the second electron is ionization energy 2. And we have to take both of these into account. Also, we'll notice that we were given the I'm just looking here to make sure this is what we were given. The electron affinity of fluorine, and we actually have two of these in our balanced equation. So these two fluorines right here. So we have to multiply that electron affinity of fluorine by 2. And that is a negative number. So, that'll be negative, 654? 650, I can do this, 656. And we add those all together and we get a we get a enthalpy of formation for this reaction of negative 2088. Also want to remind you that we used a table like this with bond energies to calculate the energy, the enthalpy of a reaction just by adding the energy of the bonds that were broken and the energy of the bonds that were formed and finding the difference in those. And remember, this is the energy it takes to break a bond, and so sometimes people abbreviate that with a D. It may be a DHH, and that D stands for dissociation energy. And so the energy required to break that bond, if it's this one, is a 432 kilojoules per mole. So if we are forming that bond, we just change the sign. And so if we add up all of the bonds that are broken, and then we subtract the energies of all the bonds that are formed, we should get the enthalpy of that reaction. Now remember, this is an estimate because, for example, this carbon-sulfur bond might exist in a wide variety of molecules, and in different molecules it may have a slightly different dissociation enthalpy, but we're going to come fairly close. So here are the problems you had. There's the problem we did in class. Here are the problems you had in your assignment. Problem number 54. Notice that some of the bonds remain the same between reactants and products. The book suggests that sometimes if you want to save time, you could only break and form the bonds that are involved in the actual reaction. That way, but if you include them on both sides of the reaction, they will, of course, cancel each other out. So in this particular problem, there was one carbon-nitrogen triple bond and two hydrogen-hydrogen single bonds. Oh, there they are. I wasn't seeing the coefficient. And I'm looking to see here. Okay. This bond and this bond, they are saying, was present in both, and so they've just left it out of the calculations. I think. Yeah, they've just left that particular bond out. That's what the little note up there at the top is about. This carbon-nitrogen single bond is formed. This two carbon-hydrogen bonds, these two bonds, are formed. And two nitrogen-hydrogen single bonds are formed. So we're going to add all of these. That's what we've done down here. And then we're going to subtract each of these. Now, the way I tend to do this is subtract each one of them in a separate step. You can add them all together and subtract them, whichever works best for you. But you should have gotten negative 158 kilojoules. In this particular reaction, we have a nitrogen-nitrogen single bond right here that's broken. We have 4 nitrogen-hydrogen, 1, 2, 3, 4, that are broken. And we have 2 fluorine-fluorine double bonds that are broken. The bonds that are formed are these 4 hydrogen-fluorine bonds. So we have to do 4 times this number, and we have to do, there's the nitrogen-nitrogen triple bond that's also formed. So we have these 5 bonds that are formed that we need to subtract. So here are all of these added together. Here are these added together. Notice we have 4 of the 565 kilojoule, and we're subtracting this total, and so that should come out to negative 1169 kilojoules.